Hello, my name is Ho Kim and I am a graduate student at GIST. Today I present on analysis and validation of stiffness and payload of nematode-inspired cable routing method for cable-driven redundant manipulator. The cable-driven redundant manipulator, known as CDRMs, can adapt to narrow and hazardous space due to their high dexterity. The snake arm robot from Robotics, shown in this video, is one of the most well-known examples of CDRM. In recent years, several studies have proposed mechanisms and control algorithms to improve the performance of snake arm robots. However, the cable routing method has not changed at all. This is a schematic of traditional cable routing method. The cable of each joint connects the upper disk of the joint with the motor on the base, and they are arranged radially on each disk. However, this traditional cable routing method has limitations. First, the stiffness of manipulator is limited, and second, the load capacity is limited. To address these limitations, we proposed our nematode-inspired cable routing method in our previous research. The nematodes, as shown in this video, have undulatory locomotion like snakes due to their own muscle structure. The muscle structure of the nematode is shown in the right figure. Its muscle cells are arranged radially in the cross-sectional plane and alternately in the head and tail plane. This is the schematic of our nematode-inspired cable routing method. The muscle cell of the nematode is regarded as the moving pulley structure, and the moving pulley structure is arranged similarly to the muscle structure of the nematode. And furthermore, the two moving pulley structures are made of one pair, which is controlled by a single motor. This cable routing method allows us to improve the stiffness and load capacity of CDRM. As shown in this figure, the prototype was developed. The diameter and the length of prototype is listed here, and the prototype consists of 6 joints, each with 2 degrees of freedom. The moving pulley structure has a winding number K of 3, which represents its force amplification ratio. Using the nematode-inspired cable routing method, we define the forward kinematics of the prototype. First, we define joint space forward kinematics. To achieve a 90-degree bending angle in each joint, quaternion joints were used to achieve 2 degrees of freedom in the roll and pitch motion. To implement the alternately arranged moving pulley structure, 2 quaternion joints were regarded as a single joint set. Each quaternion joint's roll and pitch angle were represented by a modified Euler angle representation. Second, we define cable space forward kinematics. To implement the radial arranged moving pulley structure, we use 2 cable routing methods with a 45 degree of offset on the tilting direction angle. Each cable routing method was applied to a single joint set and alternately arranged on the entire CDRM. Based on joint space and cable space forward kinematics, we can calculate the relationship between end effector movement and cable length change. To validate the kinematics of the prototype, we simulate the inverse kinematics using MATLAB. An efficient algorithm known as fabric was used to solve the inverse kinematics of the manipulator with a high degree of freedom. The simulation was conducted with desired trajectory and all joint angle limits were set to 90 degrees. As shown in the video, we can validate the forward kinematics and inverse kinematics of the prototype. Additionally, we conduct experiments with the prototype to validate the bending angle. As shown in the video, the prototype has the large bending angle of over 180 degrees. This result indirectly indicates that the prototype has high dexterity. To calculate the stiffness of CDRM, we used an analytic method based on the principle of virtual work. Before calculation, the static model for CDRM was defined. In this paper, the friction and gravity effects were neglected. After some calculations, we can obtain a stiffness matrix without the pseudo inverse. Finally, using stiffness matrix, we can calculate the maximum stiffness of CDRM. As shown in the table, the equivalent stiffness calculation results are listed. As shown in the result, the amplification ratio between NCDRM and MCDRM almost 2, and the amplification ratio between NCDRM and TCDRM rapidly increases as the moving free cable winding number is increased. Based on the results, we can conclude that our proposed method can amplify the stiffness of CDRM. Furthermore, the proposed method is more effective in amplifying stiffness than the severely arranged moving free cable routing method. To validate the stiffness of the prototype, we measure the displacement caused by an external load applied to the end effector. As a result, the average stiffness was 2.5529 Newton per millimeter, with a standard deviation of 0.1350 Newton per millimeter. Furthermore, a load capacity was measured using the developed prototype. As shown in the video, the prototype had a maximum load capacity of 5 kilograms. In summary, the stiffness of the prototype was 4 to 10 times larger, and the load capacity was 2 to 3 times larger than that of other CDRMs, demonstrating remarkable stiffness and load capacity performance. As a result, we can conclude that the proposed cable routing method enhances the stiffness and load capacity of CDRM. In future research, we will improve the performance of the prototype. Thank you for listening.